Hey everyone, thanks for coming to yet another RO Theory seminar. We've got Jonathan from Stanford presenting today, and Nan will be hosting. Thanks, Jonathan. Please go ahead.
Okay, great. Can everybody see this?
Yep, we can see you.
Okay.
All good.
Great. So yeah, thanks so much for having me here. I'm really excited to talk about some of our work on learning in POMDPs with Hindsight Observability. I will say that unfortunately I got sick this week, so my voice sounds a little different than it usually does, and I'll try to keep this a little bit short. But this is work with that I did during my student researchership with Alec, Chris, and Tong at Google. So I'm the purpose of this talk will be to sort of introduce a different tractable problem setting for learning in POMDPs. And so I'll spend a good deal of the talk sort of motivating the problem setting and discussing what makes POMDPs hard in general, and why we might be interested in studying this kind of version of the POMDP problem with this hindsight observability. And then towards the end, we'll go over some of the algorithms and how we actually get some sample complexity results there. So I'm sure that most of this audience is already very familiar with partial observability in decision making, but just to review it a little bit, the main idea of partial observability is that in many decision making problems, we don't always have all of the information we need to make a good decision at any given state. There could be issues such as in robotics where our sensors don't provide complete information about the problem that we're trying to solve. There could be things like occlusions, objects that you can't see. This also comes up in, for example, self-driving cars, where we might get noisy or imperfect observations of the state from the sensors we have. And it often comes up also in healthcare and clinical settings where clinicians will have to be making decisions about patients with an incomplete picture of exactly the patient's condition in these different setups. And so it comes up quite a bit in many of these applications. It's sort of different from, kind of makes the problem a little bit more challenging than from if you were to study things with what we would call like full information. So probably the most common model for studying partial observability is the partially observable Markov decision process. And this model is pretty much exactly like very similar to a normal MDP, at least underlying it, where you have where if you're in a state and you take an action, you might transition to your next state conditioned only on the previous state and action. And you would do this transition according to what we call this transition function, or our dynamics, which give us a distribution over the next possible states that we could have. The challenge comes up in POMDPs, where rather than actually observing the true underlying state that's doing these transitions, we will only observe these observations Y here, which again might not contain all the information that we need about the state. And these will be sampled from this conditional emission function, which we denote by this O star here. So this gives a distribution over possible observations we could see given the current state that we're in. And then finally, we'll also just have a reward function, which in this talk we'll assume is known and deterministic, and it just depends on the state and action, although you can loosen this up to depend on observations as well. But yeah, basically, same setup as MDP, just you only look at the observations from the emission function rather than the states. So this is sort of the basic POMDP model, and just to review some of the progress that we've seen over the last few years in decision making. There's been quite a lot of work now in understanding reinforcement learning in MDPs in the fully observable setting. And we now have a fairly good understanding of many of these problem settings, such as the tabular case, where we have like finite states and finite actions, linear function approximation, and now a lot of work on doing general function approximation in these fully observable MDP settings. And there's a lot of great work on this, but then on kind of the side of understanding POMDPs and sort of the sample complexities we can achieve in this partially observed setting, there's been comparatively less work, but there has been a surge of interest in recent years in trying to understand POMDPs, reinforcement learning and POMDPs a lot more. Unfortunately, POMDPs are very challenging, as we'll see in the next slide. Kind of right off the bat, it's really hard to, it's very easy to construct examples where it's just not really possible to learn anything with a reasonable amount of samples. And so a lot of this work is sort of focused on trying to identify cases where we can do any sort of learning at all in a reasonable amount of samples. And we'll touch on a couple of these sort of like decodability conditions and observability conditions in the next few slides. But it's quite easy to sort of construct these simple settings where you pretty much need at least 2 to the h samples to learn anything in these settings. And we'll look at one of them right now. What we're looking at right here is just an example of right now an MDP with just 2 states. There's a good state and a bad state. And the idea is that you want to stay in the good state for your entire horizon. And if you manage to stay in the good state for the entire horizon, you get a reward of 1 at the end. But if you, at any time, if you go to the bad state, you get stuck in the bad state and you get a reward of 0 the whole time. And the only way to stay in the good state is by taking a very specific sequence of actions in order to stay in that state, kind of keeping up with this this A star at each time step that you interact with this. And so as an MDP, this is not a particularly difficult problem. But if we consider this as a POMDP, where maybe we say that our observation doesn't reveal any information about what state we're in, we have no idea if we're in a good state or a bad state, really the only thing you can do in this setting is just try to play every possible sequence of actions until you manage to find the right one. And so this is going to require exponential in the horizon in order to figure anything out in this setting. So a lot of work over the last couple of years has sort of focused on trying to find conditions about the POMDP such that we can still, do some kind of learning, some kind of non-trivial learning in these different POMDPs. And a lot of this work has sort of focused on what information can be revealed in the present observations that you get in order to tell you a little bit about what the actual underlying state was. So in the previous example, the observations were constructed in a way that you didn't learn anything about what the underlying state is, but maybe there are some conditions we can put on the POMDP in order to figure out, how, in order to figure out like what state we're actually in. So one really interesting area is sort of this decodability condition. And the idea here is that each observation that you get is generated only by one latent state. So you can't get them confused. In other words, you can find a function that will map your current observation directly to the state that it's coming from. And the challenge is to try to find what this function is. And so essentially, in a way, it sort of behaves like an MDP, but it still potentially gives you a lot of richness in the types of observations you can deal with in these settings. And you can relax this to say like the last k observations determine the latent state, and so on. And another class of conditions that's gained a lot of popularity recently are sort of these observable or revealing conditions. And the gist of these conditions is that the emission function, this O star that produces our observations, is well conditioned in some sense. Like the minimum singular value is lower bounded by some constant. And so some of these ideas extend to predictive state representations as well. And the main idea here is that it's not as maybe as straightforward as the decodability condition, but you can still be able to sort of tease out like what the latent state distributions are going to be based on these like this well conditioning of the emission function. And so this will sort of preclude that really hard example that we looked at on the previous slide.
I have a quick question here, just in case. So, I think this well conditioning assumption for both the POMDP and PSR case are very similar to each other. I guess for the POMDP case, it's well justified because POMDP can have a redundant representation, right? Like you can just add useless states, latent states to the POMDP without changing anything, in that case, you get like 0 singular values. So this assumption is almost just saying like, we want to get rid of the redundancy. But for the PSR case, PSR is by its very nature defining a way that doesn't allow any redundancy. So is there any, so what's the intuition that it still requires these kind of assumptions?
Yeah, that's a good question. So I'm not too familiar or remember that much about the PSR case, but at least for at least for the POMDP case, I mean, I think that that's the right intuition. You're just trying to kind of rule out these cases. I don't know, maybe um, others have thoughts about the.
Yeah, I guess in general, I think this, if you map this to the MDP case, I think it's somehow maybe related to something like a reachability or some kind of something like that, right? And in the MDP case, it took some time, but we eventually, gradually get rid of these parameters in various places. Yeah, I'm just being also thinking recently about this, but yeah. Anyway, yeah, just a side comment.
Oh yeah. Thanks for that. So what you'll find in many of the bounds that are produced by these observable or revealing conditions is that your sample complexity will depend inversely on these parameters, at least a lot of the upper bounds that you see. And so that's kind of how we are able to get this like quantitative version of whatever sample complexity results you're interested in. Um, but again, I'll kind of emphasize that a lot of this is about trying to restrict the POMDP that we're studying to kind of reveal some information in the present observations that we have. Again, we can like kind of take the last K observations or something like this, but for the most part, it's kind of what can we tell about our latent state from the current observation. So this has motivated us to sort of ask beyond these sort of immediate conditions on the observations, are there other conditions that allow for efficient learning in POMDPs? And more specifically, do the motivating practical applications of POMDPs suggest that more can be gleaned from the data itself? And I'll start, trying to answer these questions with basically an example. An example application of where we might frame a problem as a POMDP, but potentially have some information available to us that can help us learn potentially a lot faster. So this is an example on data center scheduling, and this originally came from a paper by Sinclair et al., which came out last year. And the idea here is that you have a data center, and people will submit jobs to this to the queue, and once in the queue, these will be allocated. The different jobs will be allocated to some finite set of resources that you have, which are going to process each of the jobs. And once they're done processing, they go into like this list of completed tasks when they're finished. And the idea here is that the sort of challenge to this problem is that you don't know when the different jobs are going to arrive because people will just submit them at certain times, and you also don't know how long each one is going to take in order to process. So these things are basically unknown to us to begin with. But if we knew this information, we could potentially just compute an optimal plan in order to solve like what's the best way to allocate these different jobs to the different resources that we have. And one way that you can frame this, it's not necessarily the only way, is as potentially a partially observed problem where these are this arrival time and job lengths are part of the state, but they're just not observed. But what's interesting about this is that once all the jobs are completed, such as at the end of the day, the problem does become fully observed in hindsight, where we know now when all of the jobs were submitted to the original queue. We know how long each of them took to process for the previous day. And now we can potentially use this information to help us learn a little bit faster or maybe a little bit more efficiently when we need to restart this process of scheduling in the next day.
Jonathan, like for this one, yeah, I think I read your paper, right? And I think that there are very obvious robotics applications where hindsight observability makes a lot of sense. For this one though, I think there's another line of research in the literature in the recent RL works that also motivated by data center scheduling problems. For example, like the study of exogenous MDPs, right? So in those cases, I mean, I think without looking at, so if you just look at the standard modeling of the problem, it's a Markov problem, right? I think it's a Markov problem. You can call those like unknown job arrivals, which are usually viewed as exogenous random variables. But is it really useful to pose this as a POMDP? Because yeah, you know what I'm saying? Because it's like it's not something that you really should be aware of, right? It's like the entire point of your policy is to be robust against these kind of unknown and hard to a priori predict kind of fluctuations in demand.
Yeah, that's a great point. So yeah, I definitely don't think that in uh, that for this particular example, like there are ways to construct this example such that you are able to maintain it as like truly just a Markov process, and um, then you can sort of get around any issues that you would have if you were to try to frame it as a POMDP or something. But there may be some kinds of representations that you take for this problem where it kind of looks it would essentially look partially observed in this setting. But yeah, you bring up a good point. I think definitely there are other ways to frame this, and we'll see a couple more examples on the next slide of ones that perhaps look a lot more. It's a lot more obvious that there's not really a Markov version of the problem. But yeah, I think that this paper by Sinclair et al., for example, they were studying this as like setting it up as like an exogenous MDP. Okay, so but the main point I guess that I want to get across here is that there's some difference between what we have available basically when we're actually training the model, like once we have all the data available to us, and what information we have available when we actually have to execute the policy at test time, where we don't have this information about when necessarily the jobs are going to arrive and how long they're going to take to process. So there are a couple of more examples that I want to touch on, and I think some of these maybe will be a little more obvious about why we would set it up as a POMDP in some of these. So we talked about this data center scheduling problem or resource allocation in general, but as it was brought up, sim to real learning is definitely another area where for example in robotic setups where you really have some information available to you during this training phase that's not available during the testing phase. So in this problem, the sim to real problem basically refers to the idea that I want to train my robotics policy in the simulator, and then I'd like to transfer it into the real world. For example, using camera inputs, let's say for a sensor. But during the training phase in the simulator, I actually have a lot more information available to me that I don't have when I need to move to the real world, which is that I can tell where all the objects are, I know what their orientations are, and there aren't necessarily these issues with having occlusions or something like that due to the camera, because you can tell from the underlying state where everything is. And so this is potentially very helpful information to do learning a lot faster in the simulator versus like the information that we have at test time to actually execute the policy. Another place that this sort of sim to real comes up is in constructing game playing agents. Let's say that we're playing a game where when at test time we only have a limited view of the entire state of the world when we're actually playing or competing in this game. But then during training, we can actually use the game state to give us a lot more information about where all the units are or what might be the best strategy in this case. But in the end, we would still like to be able to produce an observation-dependent policy that's really only working with the present observations. This has also come up in training these sort of fast-paced rally cars. This is some work that came out of Georgia Tech, where the idea is that they would like to produce this mini rally car that's able to use, once again, kind of like low-cost camera inputs to actually run this in the real world. But during training, they're going to use more sophisticated state estimation techniques and more sophisticated sensors in order to actually train the policy, and then they'll distill the actual optimal policy that they compute with this extra information into the observation dependent one to potentially accelerate the learning that they can do in this setting. And finally, in some healthcare applications, this can come up quite often for cases where, let's say we're screening for diseases, and we have some kind of imperfect tests that we can run on different patients, but they're not they're not totally accurate. They may return like false positives or false negatives. But then for some patients, we can also run sort of a perfect information test, like a biopsy, which definitely tells us what the condition of the patient is. And in these settings, that can help inform us what was actually the condition of the patient when we were running the more imperfect tests to help us calibrate them a little better. So motivated by these different applications, in this paper, we propose this notion of hindsight observability, which is a way that we want to formalize this idea that at some point along the way during our learning process, in our partially observed setting, we're able to get more information to help us with this with the learning process. And so the way that we're going to study this is basically consider two different phases. In one phase, we kind of have the test time phase, and the second phase is our training time phase. And test time is pretty much exactly the same as a normal POMDP. The latent state is hidden, and the learner has to make decisions entirely based on the observation action history that it's seen so far. So it's just a normal POMDP interface at test time. But the difference happens at training time, which is that we assume that the latent states of the POMDP are revealed to us after deployment or in hindsight. So the learner can potentially use this knowledge of the latent states to update its policy for the next round. So there's this nice graphic here. We can sort of take a look at what this means. We deploy the policy, we collect our actions and observations that we get from deploying it in the world, and then we are either able to compute or we're given the latent states to us in hindsight in the next phase, and then we use all of this information to update the policy. So to see what kind of gains we can potentially get from this setup over kind of treating this as a fully partially observed problem, we'll start with the finite hindsight observability case, or I'll refer to it as the HOMDP from now on. And in this case, we'll kind of study the simplest version of it, which is this sort of finite or tabular setting. And here, just kind of recalling some notation, we'll have a state space, which has a finite number of states, an observation space with a finite number of observations, and the same for an action space. So kind of the sort of standard setup for this most simple problem. And the algorithm that we'll run in this setting is what we refer to as hindsight optimism via bonuses. And the algorithm is actually very simple. All we'll do is maintain maximum likelihood estimates of our transition and emission functions. So these are literally just taking the counts of how many times do we transition to X prime, given that we were in state X and took action A. How many times do we observe observation Y, given that we were in state X? And so we'll just compute these estimates of these distributions, and that'll kind of be it for the MLES, for the maximum likelihood estimates. And then the only thing that we'll do from in this next phase is basically just compute a reward function, which is bonused in the which has bonuses in the directions that that we're most uncertain about. So we'll just construct this reward function from the original reward function plus a bonus that we get for whatever uncertainty that we have about the number of from the number of samples that we've collected at state X, and then another bonus for our uncertainty based on the number of samples that we have from being in state X and taking action A. So this is going to correspond to our uncertainty in the transition dynamics, and this is going to correspond to our uncertainty in the emission function. So it's fairly straightforward, and if you're familiar with like lots of just normal MDP approaches, or at least for the tabular case, it looks very similar to those. We're just accounting for the having to estimate the emission function. And then all we'll do from this point on is just compute what the optimal policy is on the POMDP that's specified by our estimates of the transition function and the emission function and the reward function, which is bonused in these uncertain directions. And so we can use whatever POMDP solver that we might have, or approximate solver. In general, it's doing this calculation might be difficult, but we'll mostly focus on the statistical aspects of it. So something to note about this is that we don't need to worry about like making sure that we see certain histories or making sure that we see certain observations. We can kind of play it entirely in terms of what we see from the latent states that we visit. And so the fact that we're able to observe the latent states after the fact allows us to do a lot of these calculations here that you wouldn't normally be able to do in a general POMDP where you don't have access to the latent states.
Right. So that I think that what distinguishes this approach from a baseline that you run reward-free exploration over the underlying MDP and then just estimate the model and then do planning in the estimated POMDP, right? So there you would need some kind of reachability in the latent state space to reach, and you need to literally reach everywhere.
Yeah, that's a great point. So the setting where that's definitely one thing that we could do, which is run this sort of like reward-free method. One thing that I will point out about that setting is that in that setting, you would basically require that the latent states are like simultaneously observed during the training phase, which is definitely something that can be done. There are some of the examples that I mentioned before, like the sim to real training is exactly one of those settings. You kind of like simultaneously have access to it. We'll sort of see in a couple of slides that having access to this, having access to the states like simultaneously during the training phase won't actually help too much in terms of sample complexity, but definitely.
I see. Can you remind me what's your setting then? It's like when you online interact with the POMDP during training phase, what information do you have access to?
When you interact with the POMDP during the training phase, anytime that you're taking actions in the POMDP, you only see the observations and actions. And it's just that when you terminate the episode is finished.
And then it's revealed to you.
Only then is it revealed. Yeah.
But it's per episode. It's not after the entire training, then everything is revealed to you.
That's right.
Every single episode, then you see the latent states.
That's right. Yeah.
Okay, got it.
But yeah, that's definitely a great point. And we'll revisit that a little bit in the next couple slides. So the sample complexity result that you can get for running this hindsight optimism algorithm is basically that for any POMDP with X latent states, Y observations, A actions, and K episodes of training, we can get a guarantee or a bound on the suboptimality that scales as square root of XY plus XA over K. And then we also pay for some things depending on the horizon, but we won't worry too much about that. So something to note about this bound is that the second term is sort of this, can be viewed as sort of this natural extension of the standard MDP bounds that you would achieve in this setting, aside from the age dependence. And the only thing that we're seeing extra here is that we have additional, this additional term that depends on XY, which is essentially what we pay for having to estimate the emission function in this setting. But the thing that the kind of main takeaway is that despite the lack of information that we have in the policy, the lack of information that we have on the policy at test time, where we don't actually observe the latent states when we deploy the policy, there's no dependence on anything like these observability parameters that we had talked about in the earlier slides, like this 1 over alpha. Here we can get basically dependence on that looks very much like sort of your standard MDP bounds as a result of making use of this this latent state information. So a natural follow-up question to this is, whether we're actually able to, whether we can substantially improve upon this. And so we also constructed a lower bound for this setting, which suggests that we can't make substantial improvements to it, at least in terms of dependence on this XY term. This theorem basically says that any algorithm that outputs a policy over k episodes is going to have error that's, we can find a class of problems where we're going to have error that's at least this square root xy over k dependent. So we're going to basically have to pay this linear and xy term that we're dealing with. So this is an information theoretic lower bound, so it holds for any algorithm we can design, but it also suggests that this hop B algorithm that we have, this hindsight optimism algorithm, can't be substantially improved, at least in its dependence on xy. And then sort of your standard lower bounds for MDPs would also suggest that that XA term is not substantially improvable either, although you might be able to get improvements over the H dependence. So kind of going back to the question before about this sort of alternative setting where maybe you have oh, sorry, I should say one more point on that is that when we had written this paper, there weren't too many lower bounds that were looking for like dependence on X and Y. And most of it was kind of focusing on the observability parameters, but at the same, there was some concurrent work at the time that made pretty substantial progress on this around the same time, and that's cited here. But the thing that I'll kind of go back to that earlier question about this case where what happens in the setting where during training time you have your latent states revealed to you simultaneously. This happens in the sim to real case where when you're actually deploying the policy during the training time, you don't have to wait until the very end to see all the latent states. You can actually make use of them in the current moment. And you could potentially run something like a reward-free algorithm that was mentioned, and do your exploration there, and then try to just compute what the optimal policy is. Basically, what this this lower bound will also hold in the setting where the latent states are revealed simultaneously. So this suggests that being able to have that information at the same time doesn't just substantially help with improving your sample complexity. It's kind of due to the fact that in the end you have to work with a partially observable policy when you actually deploy the final policy. So we unfortunately can't get that much, at least statistically, out of making use of the latent states during training. But there are definitely other things that that could be helpful for. For example, computationally, it might be a lot easier to run a reward-free algorithm and then just like compute one POMDP policy in the end, rather than having to do this like at every stage. So there are definitely other benefits, but at least like statistically, there's not much that we could potentially gain from that. So the last result that I'll go over is sort of a result for doing generalization or function approximation in POMDPs. And the idea here is that our previous bounds sort of apply in these finite settings where we're trying to get a nice characterization of what the sample complexity was in these fairly simple settings. But in practice, we'll often want to do some sort of function approximation. So we'll go over a model-based version of this, where the idea is that we have the idea is that we're going to try to use these function classes, script t and theta, to try to estimate what our transition model is going to be and what our emission function is going to be. So the assumption that we'll make in this setting is that t star, which is the true transition function, admits a low rank decomposition with rank d. So that basically means that we can rewrite the transition function as this inner product between these two feature vectors phi and psi. And these both have dimension d. And then the other assumption that we'll make is sort of your standard realizability assumption. T star is in t and O star is in theta. And the algorithm that we'll use for this setting is also fairly simple. It's not too different from excuse me. It's not too different from similar algorithms that you would see for MDP style cases. And the idea is that we're just going to maintain these version spaces of plausible transition and emission functions, and then we're going to update them based on our maximum likelihood estimates. And so this algorithm we call hindsight optimism with version spaces. And so we're just, as I was kind of saying before, we're just going to, keep around around a confidence set of possible transition functions that are like, at least as good as the best one that we have that we could find up to some error term. And we're going to do this for both the transition functions and the emission functions. And then what we're going to do is just basically take a max over these sets and find the policy that optimizes this. That optimizes the value for this setting. So it's just going to be kind of our standard optimism over these confidence sets that we maintain. And the result that we can get for this setting is one that no longer has to depend on the number of latent states that we have, or the number of observations that we have. Instead, we can get a bound where the suboptimality scales as square root d times the complexity of our function classes over k. This is for the case of finite function classes that we're using for our approximation, but you can easily extend this to more other standard notions of complexity of the function class. What's interesting about this is that this is probably an even easier setting than the finite setting. And even though it's a generalization, in the finite setting, we kind of wanted to focus on trying to get as tight of a bound as possible in the setting. And so it sort of leveraged kind of this alpha vector analysis and bridging that with sort of a UCB VI style analysis. But in this setting, we kind of went for the simplest thing that we could do to still get dependence on the rank and the complexity of the function classes. And so it's actually a lot easier to derive this result than the previous one. And yeah, as I was saying before, there's no explicit dependence on x and y, which is in contrast to the finite bound. And we also, again, don't have this dependence on any of the observability parameters similar to the previous one. Finally, something interesting perhaps to point out about this setting is that we don't actually require any structural conditions on the POMDP or POMDP itself beyond stuff on the latent MDP. So we really only just assume that the latent transition dynamics have this low rank decomposition, but otherwise, like everything else, kind of can be fairly general in this setting. So there are some open problems and questions perhaps to address beyond the ones that we studied in this paper. Naturally, this problem setting I think is set up very well for the offline setting, since you might imagine that you have a very large data set of interactions, and you're also able to compute what the latent states are, or you're given what the latent states are, and you just want to derive some policy that is going to work in the partially observed setting. So I think it's a very natural setting to perhaps consider the offline. Setting. And then there is, of course, I think a sort of natural extension is, these ideas of like weak versions of hindsight observability, where the entire state is not revealed, but some additional information is revealed at training time, and what gains can you potentially have in that setting. I think there's been a couple of works actually that came out afterwards that are trying to address these problems, and there's some really interesting results there. Definitely, I think this is very well motivated. For example, the healthcare application that I was talking about before, about screening for diseases. We may only get perfect information tests for some of the patients that we're interested in, those ones that undergo like a biopsy. But for other patients, we might not always be able to get their perfect information, since they might they might test negative in their like imperfect test. So I think that's definitely a really interesting direction to potentially pursue. And finally, I there's also for this case of function approximation or generalization, I think there are potentially things to be done in this setting where we'd like to have sort of tailored structural conditions for POMDPs or in general POMDPs, since you might be familiar with kind of other versions of understanding the complexity of MDPs. you might use like a, have that your Bellman error has like this low rank decomposition or something like that. But in the HOMDP and POMDP setting, we really have to reason about value functions in terms of the kind of these history dependent value functions as opposed to these state dependent value functions. So even though the state is being revealed to us, we still need to like kind of do all of our analysis with the history dependent value functions, since those are the ones that we actually deploy in the real world. And I think it would be interesting to perhaps consider structural conditions that are more tailored towards history dependent value functions and potentially are more general than the ones that we considered here in this work. And of course, lastly, I think that trying to find computationally efficient methods for trying to do this, or approximations, is of course a really important direction to further explore. So with that, I'll just summarize. In this work, we studied the notion of hindsight observability, which characterizes partially observable problems where latent state information is revealed to us in hindsight. And we proposed several new provably efficient algorithms for this setting. And we're able to prove that they get sample complexities that are independent of these observability parameters. Yeah, thank you so much for your time, and I'm happy to take any questions.
Yeah, thanks. One quick question. So for the computational efficiency, so the problem with your approach is that you need to solve optimistic POMDP planning, essentially. Or actually just POMDP planning, right? Because optimism is, at least in the tabular setting, is already in there in the reward bonus. So you just need a POMDP planner.
Right. Yeah. That's exactly right.
But the general function approximation version is worse, because then there you really need optimistic planning.
Yeah, definitely. That's exactly right. For the finite case, yeah, we just need access to a POMDP planner, which of course is still a non-trivial thing to have access to, of course.
Well, but I mean, like, you're dealing with POMDP. What else can you? Right?
Yeah.
I think POMDP planner is like a minimal computational oracle that everybody would need. Right, because even if the POMDP, let's say you've done all the learning is given to you, what do you do? Well, you do planning. Yeah.
Exactly.
Yeah. Does anyone else have questions?
Okay, can I ask a question?
Go ahead.
Yeah, very good talk. So I'm interested, have you think about like posterior sampling based algorithm on this setting?
I have not yet, but I think that's a really interesting direction too. But yeah, I don't know too much about how exactly we might do that. But yeah, I think that's definitely an interesting possible direction to consider as well.
Okay, thank you. Yeah, I think your algorithm is a more optimism based. There's a posterior sampling might empirically work better, even though the proof for the regret and stuff it usually kind of follows. But empirically, it could have better performance.
Yeah, definitely. I think I don't know too much about posterior sampling in the partially observable case, but yeah, I think there's of course quite a lot of work on like trying to do approximations of posterior sampling in MDPs, and yeah, definitely could be a lot more practical. Yeah.
Let me shamelessly plug here. I have a paper just uploaded on arXiv on posterior sampling on POMDP.
Okay. Nice. Okay, I will check it out. That sounds
if you're interested. Okay.
Definitely, yeah.
Just search my name, find it.
All right.
Okay. Thank you.
Thanks.
Yeah, I was also wondering if the hindsight observability, do you see the benefit of it in your regret bound compared to if you did planning for a POMDP?
Yeah. So it'll come up in and I'll maybe perhaps go to this example here. For example, in this setting, if this is an example that I was going over where you have like when you actually deploy the policy, you have no idea like what state you're going to be, what state you're in, because the observation is basically just a trivial observation. It doesn't present any information. In this setting, the you'll have to sort of pay for this like 2 to the h. Like there's kind of no way to get around it. But if you're given these, these late state observations, you can sort of get this this bound that's going to look more like your standard MDP bound, and you're not going to have to pay for this 2 to the h. So that's kind of like one example where like if you were to treat it as just totally a general POMDP and not make use of this information, it's going to be really hard to learn. But if you're able to use this, then it can be a substantially easier problem.
Okay, well, I got the intuition of it, but I was just wondering if you had like a theoretical result that says that using this sort of hindsight information or state information, like in the training phase, actually formally helps.
Oh yeah, so I guess we would maybe defer to like other results in this setting. So like if let's say, for example, there's work in the in sort of the observable or revealing cases where you kind of need to have this dependence on like 1 over alpha, or sorry, let's go to this one. You kind of need to have this like 1 over alpha dependence in the regret bound that you're able to get, whereas the results that we can get for let's say for the finite POMDP setting, this is regardless of what that alpha parameter is, we're going to get a regret bound that that looks like this, where it scales as xy plus xa over k. So we're not going to have like the 1 over alpha dependence.
What's alpha in that case?
Alpha is like sort of the like well conditioning of the emission function. So in the case where like you kind of get no information about your states or something like that, or then the alpha is going to be 0, and the smaller it is, kind of the more poorly conditioned it is, and the harder it's going to be to learn in the settings. So there are lower bounds that depend on 1 over alpha.
So does it just mean that in hindsight observability you won't be using these emission function? I mean, these alpha things won't come into the picture. That's what you're saying, right?
Right, exactly, yeah.
Okay, so it's just dependent on the state dynamics and everything else.
Mm-hmm. Right, yeah.
Okay, thank you.
Yeah.
Marco has a question. Can you just speak up?
Oh, yeah, sure. Thank you for the talk. Very nice. I have still a question on like computational tractability. Like even if you can compute this by hat with like a computationally tractable oracle, wouldn't be representing this policy still a problem? Like it should be like a general optimal policy for POMDP. So I guess it's like dependent on the history of observations, right?
Right. Yeah, that's absolutely right. The policies that we assume to be able to compute are like history dependent ones. So they like depend on like everything that you've seen so far. But so yeah, this is definitely kind of as in general for POMDPs. This is could be quite difficult.
Well, I mean, well, I guess there are 2 things, right? So one is once you know the POMDP dynamics, you can start maintaining belief states, right? And we know that the optimal policy only needs to depend on the belief state, and I think in for example, in the finite case, if your number of belief states is small, there may be even more structured representation, right? Because you can probably write down the Q function as as a function of like expected value on the latent states, and then do some argmax over there. So probably like in the hybrid case, you can have a 16 representation. Like even in the general case, let's say you need a planning oracle or something like that. Practically speaking, like when you do the planning, like you probably also do some function approximation also over to do that, and you probably like come up with an approximate optimal policy, but that belongs to some succinct policy class, right? So that'll be how you would circumvent the issue that the complexity of specifying even the policy itself is too large.
Great, thank you.
Any more questions?
I think I'll stop recording now and we can carry on with the informal discussion.